Hello friends, welcome back. In one of my earlier videos, the exponential function e, I have missed the derivation of the Euler's identity, which is really very interesting. So in this short video, I'm going to derive this very Euler's identity e to the power I theta is equal to cos theta plus I sin theta. The procedure is very interesting and I hope you will like it. Leonhard Euler was born in Basel in 1707, a border town between Switzerland, France, and Germany. He is one of the great mathematicians and certainly the most prolific scientist of all times. Euler played with formulas like a child playing with a toy, making all kind of substitutions until he got something interesting. Often the results were sensational. He took infinite series of exponential and boldly replaced the real value variable x in that equation with the imaginary value I theta and got something interesting that we are going to learn now. We already know that derivative of e to the power x is e to the power x. Now he expressed e to the power x as power series. You can observe a0 into x to the power 0, that is 1. So not written here. A1 x to the power 1 plus A2 x to the power 2, so on and so forth, an x to the power n. Now if we substitute this x equal to 0, e to the 0 will be 1 and all coefficients a1, a2, a3 will be annihilated because x is equal to 0 and the remaining will be only a0. So e to the 0 will be a0 equal to 1. Now he took derivative of e to the power x and obviously derivative of the power series or polynomial expression of the same, and he obtained on left hand side e to the power x is e to the power x, derivative of a0 will be 0, derivative of a1 into x will be simply a1, derivative of a2 into x square will be twice a2 into x, so on and so forth. X to the power n derivative will be n into x to the power n minus 1 times an. Now again what he did, he substituted x equal to 0 and e to the 0 equal to 1. This time it is a1 because all coefficients of x will be annihilated because x is equal to 0. So here we have a couple of interesting equations which are highlighted on your screen, and we have a couple of constants which we have already evaluated. A0 is unity and A1 is unity. Now let us compare these major two equations, and you can observe here that coefficient 1 is balanced, coefficient of x on left hand side is 1, on right hand side it is twice a2, coefficient of x square you can compare, coefficient of x cube you can compare. For these two equations to be equal, all coefficients must be balanced. This offers us relations like a2 is equal to 1 upon 2, which I am writing as 1 upon 2 factorial, a3 is equal to 1 upon 3 factorial, and so on and so forth. You can observe that an is equal to 1 upon n factorial. Now here I want to make a contention that a0 we are writing here and 0 factorial I want to state it is unity. So this a0 I can write 1 upon 0 factorial and that will be 1, and this a1 I can write as 1 upon 1 factorial. This a2 is 1 upon 2 factorial, a3 is 1 upon 3 factorial, and we have generalized everything that we can. So an is equal to 1 upon n factorial. Now I want to club these equations together. So I'm rewriting the equation that we have just developed in the last slide, and all coefficients an that we are having here. An is equal to 1 upon n factorial. So a0 is 1 upon 0 factorial, a1 is 1 upon 1 factorial, a2 is 1 upon 2 factorial, so on and so forth. We can generalize this as summation x to the power n upon n factorial, where n is rolling from 0 to infinity. Actually, it is Maclaurin series, not a kind of Taylor series. Now, this we can simplify as e to the power x is equal to 1 plus 1 into x. So simply x plus x square by 2 factorial, so on and so forth. Now what Euler did, he replaced x by I theta, and then he obtained something like this: 1 plus I theta square upon 2 factorial, I theta cube upon 3 factorial, so on and so forth. I want you to remember that I square is minus 1, I cube is minus I to the 4 is 1. So let us substitute and collect real part and imaginary part, and collectively we can write e to the power I theta as series of cos of theta plus I times series of sine theta. So this is how he reached to the equation which normally we look at as an identity, but believe that this equation is a very valid, very interesting and a beautiful equation that Euler has given us. Once again, we shall try to reach at the value of x through this discussion. E to the x, this Maclaurin series we have at x equal to 1. E to the 1 will be simply e. This is sum of 1 plus 1. You can imagine here it is 1 plus 1, 2. This is half 2.5, and we are adding something and something in this series which is of decreasing value. So this infinite series is going to converge to some point which is little greater than 2.5. So here you can see I have displayed 5 terms, and if you sum together these 5 terms, you get a value of e like this. And if you do it for infinitely large number of terms, calculus is handling this problem really for n equal to infinity. That turns out to be 2.71828818. I'd like to mention that in mathematics, Taylor series or Taylor expansion of a function is an infinite sum of terms that are expressed in terms of function's derivative at a single point. The Taylor series is also called as Maclaurin series when 0 is the point where the derivative is considered, after Colin Maclaurin, who used extensively this special case of Taylor series in the mid of 18th century. In conclusion, if you find this video informative and engaging, don't forget to give it a thumbs up and hit the subscribe button below. Feel free to share this video with like-minded individuals who might find it valuable. Your support means a lot. Thanks for watching. Until next time.